Okay, welcome everyone. So first, take note here on May 27th, Monday, that's in 2 weeks. Next week there is Pentecost, public holiday, and the week after I will prepare an online recording for you to watch. That will be the second and only the last time that we have to do it this semester this way. And yeah, so you don't have to come here, and after that it will be regular lecture again. Good. So last time we have looked at the different purposes that linear regression may take, including that we want to fit a hyperplane over our predictor variables to explain the response variables. So this was the good fit. Or we want to estimate parameters to understand very well how we have a response based on the change of a predictor variable. Or we want to have a good prediction, and we may want to learn about the significance of our representation. And well, depending on what we want to do exactly, we will use different tools, many of which come from statistics. So fitting a hyperplane, that's something we already looked at the last time. So I can go very quickly over this. We had this multivariate theorem that basically related a linear transformation to the change that arises then for the resulting random variable when some input was already from a normal distribution. So if before we had a certain input and this input undergoes then such a linear transformation, the mean will be shifted. That what happens here is shifted and linearly scaled, and the variance will also be modified if we had a covariance matrix sigma here, and then we have such a linear operation which consists of a bias plus a linear modification of another random variable. Then this matrix that works linearly on this vector will influence the covariance matrix in this way that d sigma d transposed leads us to the resulting covariance matrix. And when we looked at how we solve our system with linear regression, this implies then that our estimated beta hat depends, of course, also on the underlying true distribution. And the nice thing is that if our assumptions about the generating function is fulfilled, then the expected value for our beta hat has the same mean as the original function. Right? The original function is described by beta. We don't know it in general. We do our analysis based on the samples of the data that we have observed. And then the expected mean is the very same. The expected mean, of course, when we do the sample, it doesn't mean that we actually get the expected mean. We will get something close to the expected mean usually. And how close, this is determined by the covariance. And again, using our machinery and this multivariate theorem, we basically arrive at the variance of our original function, and then x transposed x to the power -1, which means overall our beta hat is normally distributed with a mean of beta, which is the original true inclination of our function, and the original variance but times this inverted matrix. And as we have more and more data, this means this covariance becomes smaller and smaller and smaller, meaning we better and better approximate what our original function was. Now, what if we want to have a good parameter estimate? How can we characterize that? So let's just look at the simplest linear system we could have. The simplest linear system would be y equals beta 0 plus beta 1 x. And what we can do is, I mean, the x's are from an arbitrary interval, of course. We can standardize this whole equation. We can re-represent our x's to represent them as some x star, where we look at the x's and we determine an average x and say that we want that our standardized representation is around an average value of 0. So we do this by transforming the original x's and subtracting the average value. So x star in average will be in average 0. Now, what we can also do in order to have a standardized representation, we can broaden or shrink the distribution of x's. So if our x's vary a lot, they have a certain standard deviation, which may be very large. We just divide by the standard deviation of our x's, which means that the new standard deviation of our x stars will become 1. The same, of course, is true if they vary very, very little and have a very, very small standard deviation, and we divide by it, then again it will be normalized to a standard deviation of 1. So this is just a transform to turn our x's into x stars based on the average value of our x's and based on the standard deviation of our x's. Yeah, so x star average is 0, and the way we construct it, we can also define this to be our y star, where our y star is similarly recalibrated. Okay, that's also nice because then beta 0 goes away. We formulate it just in exactly this way, and now our new standard deviations are exactly 1. Well, if we now look at the correlation between our x and y's, then this correlation is exactly described by beta 1 star, because our x star is simply beta 1 star times x. And well, this, of course, this beta 1 star is then simply described by this connection between the xi's and the yi's, and this is simply beta 1, the original one, but then modified by our standard deviation of the x's, and this divided by the standard deviation of the y's. So the correlation between x and y, I mean, here we have this one-dimensional case, is then simply the original parameter that we found modified by the 2 standard deviations. So we basically see that if our beta 1 is very large, of course we get a larger correlation. But if our variation of the y's is very large, then this is again reduced. Basically, we do not, here the standard deviations here tell us we do not care about the absolute values. We care really about how the variations behave relatively to each other, which makes sense, right? So if I have a linear connection and I have large input values and I get large output values, then this is the same kind of strength of association as if I have very small input values and very small output values. But in order to talk about small and large, we must have normalized them. Yeah, because if I add 1,000,000, then this does not modify really the strength of correlation, since this is just a constant factor, a constant bias. Okay, and let's jump over this because we will then talk longer about point 3. We can talk about the uncertainties and the significance. So the question may be, is a certain predictor variable relevant? Is some xj relevant? And the null hypothesis is that it's not relevant. And if it's not relevant, that means that the best beta j value would be 0. Right? So, I don't know. Does the shoe size influence your hair color? Yeah? So, if there is no correlation between the two, then your hair color would be independent of your shoe size. And the shoe size would be irrelevant. So that's the null hypothesis, that we would have a beta j which would be 0. Alternatively, if the beta j is different from 0, then your shoe size would somehow influence your hair color. Now, when we have these hypotheses, we can look at the predicted beta j, and this beta j under the null hypothesis will be sampled from a normal distribution, because even if there is no connection between shoe size and hair color, there will be statistical fluctuations. And due to these statistical fluctuations, of course, we could observe a non-zero beta that might suggest your hair color would be influenced by your shoe size, which of course is a rather stupid assumption, but the point is, just because I select certain subset of people, that this might hold true, though with a very small beta perhaps, or even a negative beta. So we would expect that there would be a normal distribution even given this hypothesis. And of course, given that if it's really 0, the more data that we have, the smaller we would expect this beta should become, because if they're really independent, I have a lot of data, there should not be a strong signal between shoe size and hair color. So this is exactly as we have described it before. The larger my data matrix X is, the less this kind of standard deviation should influence how beta deviates from 0. Of course, I could have also put this here into my variance. Yeah? This is just a different way to write it. Yeah? I could put all this without the square root into my variance here. And I can take this then as the student t-test statistics, where I'll take this as my observations, and I test this under the null hypothesis. Well, where I put in the degrees of freedom that my student t-test would provide, and I look up the tables for my t-test statistics. This assumes, of course, again, a couple of things. Like every time when I do a statistical test, for example, it assumes that the different random variables, the different predictor variables are uncorrelated. And if the predictor variables are correlated, then I cannot use the student t-test. Or again, depends on how strongly they are correlated. The funny thing about these test statistics is that statisticians often give very precise assumptions, what has to hold in order to, such that they are applicable. And empirically speaking, they are often more widely applicable. This is the advantage. The disadvantage is quite sometimes these test statistics are overinterpreted. This is the so-called pi hacking. Have you ever heard about this pi hacking? Yeah? Can Yeah, that's general but true description. So very often, what do you do when you do a statistical test? You can never be perfectly sure because you always have fluctuations. So you say that with 95% probability, some hypotheses can be refuted. But with such a statement, there is still a 5% chance that although you refute it, it's still true. So you say two things are independent, though there may be some dependency, for example. You say that some drug helps, though there is a chance that it doesn't help. And this depends, of course, on the significance level that you suggest. Do you require 95%? Or do you require 99%? It also depends on the size of your data set, because if your data set is large enough, you always will find a difference between a truly zero, no correlation at all, and a statistical distribution. So this statistical tool is to be used carefully. There are other statistical tests like ANOVA on joint hypotheses when the variables are not independent from each other. Okay, so these are a bit more side notes about 1, 2, and 3. So these are more concerns of statistics. But the point that's most important for us in machine learning is that we're interested in good predictions. We want to predict a new response as a function of some new values for our predictor variables. And here we run into the so-called bias variance trade-off. I've mentioned this before, but let me define it again and in a bit more detail and a bit more quietness. So the problem of overfitting is that our model may overfit to the data given and may generalize badly to new unseen data. And the problem comes from the estimator variance. So you estimate the function, and the estimate depends on the data that you have sampled. Yeah, we always assume that, like in this linear regression case, we have a true underlying function which truly gives us data, but then the data we are given are sampled from the true underlying function. The true underlying function is, for example, the linear regression assumption is we have a straight line, but we also have noise. So this is the true underlying function. Now, we are given a subsample of data, and depends on which subsample of data we are given, we end up with these different estimators. Even if the estimators are great, like we just observed, the mean value approaches the true value. This is not true for finite sample sizes. It becomes true for infinite sample sizes. But we are not there. We have finite amount of data. So how can we imagine this? So here we have the true function, the true line. This is this one. In all three pictures, it's exactly the same true function. Now this true function with some noise has produced these data points. Yeah, and this is a different sample here, then the sample here, then the sample here. And depending on which sample you get, you will once choose this line, which is almost parallel, or this intersecting line, or that intersecting line. So what you learn will depend on the data sample that was generated. And I mean, here we have this as a very abstract case. But you could imagine it, we want to learn something about people. And well, here, we all in this room, we are a sample of people. We can go to the neighboring room, where maybe there's another lecture, there would be a different sample of people. And both times when we try to learn anything like shoe size versus age or whatever, we would get a different sample and we would learn a different function, even if there is something like a true connection of these attributes. So this is the problem, that we don't directly observe the true function with this kind of data. And now we do mistakes. Whatever we do, whether we get this sample and draw this dashed line, or this sample and this dashed line, or this one and this dashed line, we make mistakes. We do not have optimal predictions. So what are the mistakes that we do? And how can we reduce these mistakes? Well, the first mistake we could do is, of course, that we pick the wrong function. So what if we make a more complicated base function? For example, for these data points, we could assume, let's do a quadratic model. A quadratic model allows us to also have some squared parameters in our function. I mean, we did this, right? We had our feature function. We could also learn a quadratic model. So then, instead of this dashed line, maybe what we would learn would be this kind of parable. And likewise here, and likewise, of course, there. When we put in a more expressive function, or family of functions, then we would learn a different model. Now, which model will be better, the blue one or the dashed one? What do you think? Which one will produce a better performance? The dashed one will produce a better performance, and why? Okay, so if I repeat, but please correct me if I understood wrongly. So the colleague said the dashed line is better because it's closer to the true line, and the blue line would overfit. Okay, so this was one opinion. Another opinion? The true line is the one that we don't know. This is always the important thing to be aware of. Okay, you would say because here we are closer, then maybe that would be better. Other opinions? Depends on the metrics that we're choosing. Thank you. Perfect. The question is, what do we mean with better? You remember what we just said? Do we want to have the best fit? I mean, the arguments here were now about the best fit. Yeah, at least to some extent. Not fully true. I mean, you had some arguments about what is closer to the true line, which we typically don't know. This is the important thing to know. Of course, here we know it, but typically we don't know it. Then it depends on, we can judge what is a better fit to the observed data. And we can have a matrix, and the matrix is, for example, least sum of squares. And if we have least sum of squares, we can say which is the better fit. We would just measure the mistakes we make, the mistakes to the blue line. This is worse here for the blue line, but maybe better here and better there. So, well, we would have to do the exact calculation. But this best fit is just one purpose. The other purpose, of course, is the best predictions. And the best predictions means we do not just have to look at this data, we also have to look at this data, because this is a different sample from the true underlying line. Okay? So, important thing, when I ask you something about what is better, or anyone asks you, you always have to ask the question according to which metrics and what is behind these metrics. Yeah, this is a really super important question. Do we want to have a best fit? Then we will have an answer that we just get based on the data points available. But now we are interested to do machine learning. We want to predict. Now, how do we know what is a better prediction? When we looked into evaluation, then we said we always want to keep our data separate. We want to train on one piece of data, and then we want to judge the quality on another piece of data. And sometimes we even want to train on one piece of data, validate on a second piece of data, and then judge the quality even in a third step in a test with test data. So the point being that when we have a more expressive model, like the quadratic model is more expressive, a quadratic model also allows to give us a linear model. So the quadratic model will always have a better fit to our data points than a linear model just because it has more parameters. Right? Assuming that our quadratic model includes, of course, the linear model as a submodel. If you remember the feature functions, we would have the quadratic features, but we would also still have the linear features. And if there is no connection to the quadratic features, we might just learn the linear ones. So the quadratic model will always result in a better fit. However, as you have already also observed in your answers, a better fit does not necessarily imply a better prediction. Because, I mean, maybe it's exactly in this area up there, we will deviate perhaps a lot from the true underlying function. So what can we do? Because we don't know this true underlying function. All we have are data, maybe data points that we have split up in different training, validation, and test data. That's all that we have. Okay, so let's investigate what we get there. Again, notational, we typically say D is our training data set. We predict the function f hat based on our data set. So this is just saying f hat has a parameter x and it's trained based on D. And f sometimes is just f of x. What do we know in general about some random variable x? The variance of this random variable is the same as the expected value of x squared, so the random variable squared, minus the expected value of x taken as a value and then squared. So this is just statistics background knowledge. I don't derive this here, which means that the expected value of x squared is the variance plus this average squared. And what do we know about our residuals? The expected value of our residuals is 0. That's our modeling assumption. Actually, it can even be wrong, right? Because our data need not fulfill this modeling assumption, but let's assume it's true. What we know is that our epsilon squared, this is actually the error that we expect. Remember, epsilon squared was our sum of squared residuals. That's what we are interested in. And the expected value is not the sum, but it's just the average squared value. So it's the average mistake that we will do. And so this average mistake that we will do, or some average squared mistake that we will do, what is this? According to what we have about statistics in general above, this is the variance of our epsilon plus the expected value of our mistake squared. Now the expected value of our mistake is 0. Therefore, the square of it is also 0. So we have the variance of our residuals as our expected loss. Because so this sigma squared, it was our residuals were sampled from this distribution, and here's 0, so we have our sigma squared. Now we have the true function. F is true, an error-free function, independent from our data set. So the expected value of our f is just our f. So what we can do for points, we can also do for functions. Also, functions have expected values. I mean, a function is also nothing else than an infinitely large vector, right? For every x, we have a y. So that's nothing else than an infinitely large vector. And our y is our f plus our epsilon. So this is what we observe for certain data points, not for all data points. So the expected value for our y is the expected value for our f plus epsilon. And since the expected value for epsilon is 0, that's the same as the expected value for f, and so that's f. So, okay, y is the same as f. What is the variance of y? Now, the variance of y, and again, we can look up here, is the expected value of, this is just a slightly different notation than up there, y minus the expected value of y squared, or y minus f squared, and this is f plus epsilon, which is our y, minus f squared. So that's this loss, which consists of the variance, and this is what we have in the end. So when we define our function this way, our y varies in the same way that our residuals vary. Now, we don't work with our f. We work with our f hat. And this f hat, this is one that we predict with our parameters beta. So what is the difference between the true value and this predicted value of what we have learned? Well, we're interested in the square of that because that's our loss. And that's y squared plus f hat squared minus this term, right? Just binomic formulas, binomische Formeln in German. And well, we can take this apart. The expected value of y squared plus expected value of f hat squared minus expected value of this term. And now we take this apart and with the same method as before, up here. So what we get is variance plus expected value y squared for this blue term, and this red term we can take apart in this way, and this just stays here. And now we can rearrange things a bit in a clever way. So this is the same line as that line, but now I have recolored this, because when I recolor these green things here, I can take this together in this term here in the next line and just copy this and this and this and this. And again, copying this part, this f minus the expected value of f hat, expected value of f hat is here. I can move the expected value of e to the outside because the expected value of f is f. And then I get to this term. So I have here the difference between f and f hat, the true function and what I estimate squared. And now I look into what is my variance of y. This is my sigma squared, which is the variance of my residuals. I have the variance of my function f hat, and this is the loss that I produce. How far is my predicted function away from my true function. So how far my predicted function is away from the true function n squared, this is nothing else than the bias of my f hat. So my bias is how far am I away from the true function squared. The variance of f hat is just how wildly it fluctuates. And this is just the sigma square from my residuals. And how can I interpret this now? Well, the residuals, this I cannot reduce, because the residuals are like they are. The residuals come from my generating process. I have this function f, and then I put some noise on it. I cannot do away with that. It will always stay. It's irreducible mistakes that are added. And then what I get is the variance and the bias squared. And the bias is basically how far am I offset from my true function, but the variance also talks about how much does my f hat change when I have a different data sample, because my f hat always changes when I have another data sample, because every data sample I have is incomplete. Well, this is one has to be aware that these f hats here, they talk about all the different ways in which I train my function. They talk about all different data samples here and there, and every time I get a new data sample, I train my f hat, and they talk about how large the bias and the variance is. The expected mean squared error is then eventually nothing else than the bias I get. So basically I write this now, this term here. The mean squared error depends on my x's. When I compute on my data set and look at this f hat squared, so I write this here just in more details. And the variance just looks at how much does this actual function fluctuate. Now the error that I make has some irreducible component, the residuals. Even if I know the true underlying functions, I will still make this error. I mean, it's impossible to get so close, but if I had it, the residuals would not go away as an error. And now I have the model complexity. And when I am more and more complex, then I can reduce the bias, which is how far am I away from my true function. But on the observed data, and this is clear here only, on the observed data. The problem being, when I change the data based on which I have trained that, I will get another result. So, on the other hand, the variance will increase. And, well, the variance again depends on this data set. The variance, how much I will then deviate, will increase much more, because with a more complex function, I may have a more complex, like you saw this here, this more complex blue function gives me a higher outlier, so to say, here at this end. So the overall error that I will make is composed residual error that I don't talk about here, then the variance, and the bias. And the bias decreases as I increase my model complexity. I get closer and closer to the observed data points. But the way my function fluctuates increases just as this blue line that I showed you.
Just one question about the bias.
Yeah.
How would we quantify it? The way have a one and a half function and data.
So we don't know which part exactly is the bias. All that we observe is the overall error. Yeah, it's for us, this is just a theoretical instrument to think about this problem, but all that we observe is the total error. And the message basic being that if I have a very simple model, the simplest model could be I take a constant function. And of course, the constant function will have no variance at all. Yeah? If I have data points, and I pick now a constant function, then I have no variance in this function. It's constant. But I have a very high bias because the distance here is very large. If I have a very complex model, and so a very high polynomial, for example, then I have a very complex model and I have no bias because I exactly hit my data points, but the variance will be very large when I switch from one data set to the next data set. So I want to have a kind of a trade-off between model complexity and it should not be too complex and it should not be too simple. And I don't see this from the data fit because the data fit just tells me like how far you are away from the observed data. And the only way to see how large the error is that we make is by having a separate validation or test data set. So the error refers to how far am I away from the truth. Yeah. No, this refers to like, this total error has three different components. This is what we say. This error, the mean squared error, as we do in regression, has three components. And here we talk about mean squared error for regression, but actually for classification, we think in pretty much the same way. But we don't necessarily know for our overall error how this is distributed over these three components. Because we don't know the true underlying function. No? So all that we can say is somehow what we want is we don't want to have a too complex model. Okay. Now this is like very key to machine learning. And at the same time, in a certain number of situations, it has also been proven wrong. So this is the classical machine learning bias variance trade-off that you see everywhere, and which still plays a role, and which is also key to many statistical considerations. And now what have people observed? So capacity of age, this also means the model complexity. How can I adjust my model, like a more complex polynomial or a more complex model for linear regression with more quadratic, cubic components, whatever. And this is, by the way, and what is nicely indicated here, as I increase the capacity of my model, as my model becomes more complex on this x-axis, the error, sometimes error is also called risk, the training error or training risk goes down up to 0. At some point, my model is so complex, I hit exactly my data points, like a very high polynomial. But as this happens, my test risk goes up, and this is where I go up, this is where I go to overfitting. I overfit to the data sample I have pulled from my true underlying distribution. Yeah? I commit too much to my observation. And in the next room, a different set of people would warrant another observation. So this is where overfitting sets in, and then where my predictions get worse than if I had a simpler model. Okay, so this is the classical picture, and now people have started at some point, like only really just 5 years ago or so, to look at even more expressive models. And under certain circumstances, they observe now that the error first goes down as the capacity increases. Then it goes up, as I just explained to you, for the reasons I just explained to you. And after some threshold, it goes down again. So this is, for example, true for many of the deep learning models, where, for example, you have deep learning models for image classification with millions or billions of parameters, and every parameter adds to the capacity of the model. You could also say, okay, a linear, people even tested this with linear regression. You can always, when you learn these functions, over-parameterize, and when you do over-parameterize, you can also sometimes facilitate learning. It's not as simple as I can say always over-parameterize would always be better. You can also heavily overfit, but in certain circumstances, it is useful to over-parameterize. It's still an ongoing research discussion when over-parameterization is useful. If you want to have very detailed knowledge about that, you should ask Professor Steinwart from the math department. He has done research on that. I didn't, so I wouldn't claim I'm the expert on that. So this is still puzzling people to some extent. Here is something where people used logistic regression, which we will do next, to classify, and looked at model complexity. What you see here is we had some loss function, which we will look at next, and the training loss goes down as it's supposed to be. I mean, the more powerful you model, the training loss should always go down. But you also have the test loss, and that first goes down, then goes up again, and then, well, in this case, it's about the same, maybe even a little bit worse. But you have this double dip structure for a very simple task, in this case, logistic regression. You might have even a better result here than over there. It's not always the case, so here is also like a counter example. Okay, now I told you the story about having moderate model complexity. I mean, in spite of the fact that there's new research that suggests that sometimes high model complexity is good, in most cases, having moderate model complexity is better, especially if you don't have a lot of data. So, how can we reduce model complexity or limit model complexity? Well, one simple thing is when we do least square estimates, then we get often a low bias, but a large variance. So that means we do least square estimates, we adapt our function. The function is pretty good at hitting the data points, but then when I change the data set a little bit, I get a very different function. Just what I showed you graphically before. And sometimes you can improve your accuracy by shrinking some of your betas, some of your coefficients. Of course, what happens when you, let's say, even throw out some of the betas? Let's say you pick the betas that have the smallest value, let's say in a standardized setup. what do you think happens when you throw out some beta? Well, let's say you have a beta vector which is 1, 2, 3. Let's assume it's standardized, so that's also like this asterisk version that I showed you. And now we just turn this into 0 to 3. What will happen? Or I should maybe even say it's not necessarily 0, but we just throw this away and now only have 2 components. Well, what will happen? Sorry? It becomes linear, but it's linear all the time. Yeah? So originally it was something like beta 1 x1 plus beta 2 x2 plus beta 3 x3. So, and beta 0. Okay, so it's always linear. Right, so I basically cut this out. So what happens? Okay, if there was a property that somehow influenced the outcome when we throw away this property, that's true, yes. But other than that, no, the variance, or did you say decrease? The variance decreases. Yeah, the variance decreases because now with changing x's, there is less variance in the function. Yeah? We have more bias, definitely. Absolutely. So, I mean, if you go just from here to there, you see that our y equals beta x will deviate further from the true data points, obviously, because we had some influence and now we throw this away. Of course, we can also just learn with 2 and then it will no longer be 2 and 3, maybe some 2.5 and 3.5, yeah? But still, the bias will increase because we can no longer reflect the influence of x1. It will, again, the matrix is important. The bias will increase and it means a larger mean squared error in the training data set. Possibly in the test data set, it could even be better. Again, you have to be careful about the metrics, what you choose. Is it the metrics, the mean squared error on the training data set or on the test data set? So possibly, because let's assume I try to predict, I don't know, your weight based on shoe size and tallness and color of t-shirt or something like that. Yeah, there may be some fluctuations. I mean, shoe size and weight might correlate somehow, but the t-shirt color probably not. But there may be fluctuations, and you throw out some non-zero component. This may actually improve the prediction, although it increases the bias. Okay, a prediction accuracy can sometimes be improved by shrinking. Shrinking could even mean completely removing. But now the idea is, okay, maybe we don't throw it away completely, but maybe we want to reduce the influence of some components. Right? Between black and white, between throwing something out and keeping it fully, maybe we want to just lessen its influence. This is some like gray solution between black and white. Okay, so this, of course, will always increase the bias in our training data set, but we do it in order to reduce the variance of the predicted values, so there will be less dependency on all of our x values. And hopefully we do this in a way such that the prediction accuracy, the prediction means on the test data, gets better. And of course, you could, this is about prediction accuracy. You could also say when we have a smaller subset of variables, like now when we throw this out, we have only 2 variables. Maybe what we really determine is the subset of variables that has the strongest effect. And that's most important for doing a good prediction. So we could understand the big picture by sacrificing some of the details. So here is an example for that from the book Hastie. So I have here 0 to 7 variables, like x1, x2 until x7. 0 variables, of course, means that you just assume a constant value beta 0 for everything. This is very little variance, no variance at all actually, but very high bias. And so the mean squared error is rather high, or here residual sum of squares is very high. Now when you go to 1 random variable, you do a big jump in reducing this error. Well, it depends, of course, how big this jump is, depending on which variable you select. Do you select x1, x2, x3, x4, or whatever, x7? And the interesting point is, if you pick the best predictive variable, I mean, I said it's x1, it could also be x5. If you pick the best one, you already achieve like 3/4 of your performance with just a single random variable. As you add further variables, what you see is actually the performance still gets better. The variance increases. The spread from here to there is larger than it used to be, depending on which random variable you pick. And until you use all random variables, that is the best value here, but well, of course, then we just take the data set, so that we cannot observe variance, but of course it's still there. So subset selection for our random variables means we throw away some random variables, but fewer variables allow for better interpretation. In the social sciences, we're often interested in that. And this is a binary choice. A variable is either there or not there. And opposite to this black or white choice, we could also look at shrinkage methods. So let's not have a too large influence of some variables. How can we do this? So what we do with our beta hat is we are interested in the beta that minimizes our loss. And the loss is simply the true observed value minus, and this is our predicted function. The predicted function just adapts the beta 0, but the beta 1, beta 2 up to the dimensionality of our betas. Okay, so this is nothing else than the squared errors. So this is the errors, and then here we have the square. We pick the beta that is best to minimize this error, or this squared error. Now what we add is, we could say, let's limit our betas. Or to make it here, for this particular ridge regression, we limit beta square. So we limit the vector for our betas. We don't want it to be too large. What does this mean for a linear function if we limit the beta? Let's start with just beta 1. Beta 1 being less than 2. What does this mean? The slope is limited, exactly. So the slope is limited means, for example, we could not have a line which is has more slope than this one. I hope this is roughly true. And of course, when you have now beta 1 square plus beta 2 square is less than 2. Then of course, now I don't want to draw this now in this three-dimensional case, but you also limit the slope. But you allow, if there's less slope in one direction, you allow for more slope in the other direction. So what you do implicitly, you force the slope to be in those random variables where you get the best return. Now, how do you optimize this? This is an optimization problem under constraints. One method is Lagrange optimization. Later on, under support vector machines, we will look at this method of using the Lagrange multipliers. We don't do it now, but I hope you see that there are certain connections between different techniques. So what you effectively do with the Lagrange multipliers is that you take your loss function. This is the same as above here. You have the same argument, but you add this constraint as a plus lambda and then the sum of squared beta i's or beta j's. So now you no longer just minimize the loss, but you minimize the loss plus the value of these vectors. And if you pick a very large vector here, you are punished here. And if you pick a very small vector here, you are awarded here by having less punishment. So that means, there must be a good reason to have a strong slope. This slope is disadvantaged compared to this slope. And that means, of course, you look for preferably smaller slopes. Why? Well, you don't want that your function depends too much on the change of a single random variable or the value of one particular xi or xj. By the way, the intercept beta 0 is typically not regularized, so we start here at j equals 1 to d because, I mean, where you start is shouldn't be influenced by that method. It's really about how strongly the response reacts to the predictor variables, what you want to change. Okay, so this is now our new optimization. Now, when we have our residual sum of squares, which depends on our lambdas, then we can write this in our matrix notation of linear regression as y minus x beta. So x beta, with all the trick of the bias being also in there. So x beta being the prediction, y being the true value, and the difference between the two is then the mistake that we do. We square this and we write this in this matrix notation by having this vector transposed times this vector. So this gives us then a scalar. And plus lambda beta transpose beta. Beta is a vector, beta 1, beta 2, beta 3, and so on. So we have the row vector of beta times the column vector of beta. And again, this gives us a scalar, and the larger the values in this beta, the higher the punishment. And the lambda is for us a variable to adjust how much punishment we want to give. So when this is our new loss function, we can do the same analytical procedure that we did before with our linear part. With our purely linear regression, we didn't have this blue part here. And when we took this equation and we resolved it for the optimal beta, or the optimal beta hat, you remember, by deriving it, setting the derivation to 0, resolving for beta hat. That's the same you can do here, only then that instead of this black part here, x transposed x to the power minus 1 x transposed y, we also get this additional blue component here as an additional ingredient. But the way we arrive at that is exactly the same thing with computing the derivation, and setting that to 0. So what happens here is that this matrix is made a bit larger by lambda, and here I is the identity matrix in the right dimensionality. Yeah, everyone knows what the identity matrix is, I assume. Okay, that's very neat. So we say here now, let's not get a too strong response. Of course, instead of having here beta square, we could also have the absolute value of beta j. Now, the problem with this is we cannot solve it analytically like this. So what we can do is we can do some quadratic programming, we can do some stochastic gradient descent, which we will talk about later. What is the difference between these two? The first is called ridge regression, and the second is called lasso regression. So let's look at the possible values of beta. So this is beta 1 and beta 2. Let's say we solve for beta 1 and beta 2. Remember, we suggested that beta 1 plus beta 2, that was in this version, is less than some value. So if beta 1 plus beta 2 is less than some value, the two values of beta are inside of this diamond. Yeah, because let's say this is 1, 0, then the sum is 1. If this is 0, 1, the sum is 1. And if this somewhere in between is on this straight line. Likewise, for ridge, we said that beta 1 square plus beta 2 square is less than 1. Then this is a circle exactly, not a diamond. So these are the allowable regions for our betas. Now we look for some beta that optimizes the rest of the thing. So when let's say here would be the unconstrained optimal beta. And now we look, this beta that we have here is influenced, and we look for the closest point in the allowed region to the optimal value. The closest point, of course, these are circles around this point. And now, when we have this kind of diamond, the chance is high that we hit a corner. What does hitting a corner mean? It means that, for example, in this corner, beta 1 equals 0. A high chance does not mean it's always the case. If beta hat was a bit further down here, the optimal value would be somewhere here. It's not a strict requirement. It's just like in a certain area above here, the closest point will be this corner. And of course, likewise, in a certain area here, the closest point will be this corner. And if I hit such a corner, what have I done? What does this mean if I hit a corner? I eliminate a parameter, exactly. So, by basically providing this lasso regression, I often, not always, but often eliminate a parameter. And all the rest of my regression task is assigned to the remaining parameters. Whereas here with ridge regression, I very rarely would hit beta 1 equals 0. It's not impossible, but it's only really possible if beta hat would be up here exactly on the y-axis. Okay, so ridge has the advantage. We have a nice analytical solution, but lasso leads typically to a sparser feature selection. So it's easier for us to weed out less important parameters. So actually, lasso is often quite liked for that you can throw away variables, and you have a principled method to do so. You can also pick, of course, other methods, like you can take any beta j absolute value of that to the power q, and depending on what q you do, you get different allowed areas. And let's say, for example, here q equals 0.5, you get such an area. Now it's even more likely that you eliminate a particular feature. And on the other hand, if you do q to the power 4, then it's very unlikely that you eliminate one. It's more likely that you almost equally balance parameters. Now the question is, of course, what about this lambda? We have not really said how we justify lambda. Is lambda 1 or 0.1 or 10 or 1,000? So how do you go about this typically? Lambda is one of these hyperparameters in your machine learning procedure. You don't know how to set it, but you have to set it. So what do? You use validation data in order to set it. That means you try different lambdas. I mean, there are own papers that talk about how to set such hyperparameters when you explore your method. But let's even just say a typical one, a simple one is just trying to go through all possible value combinations with a certain grid-like structure. So grid-like hyperparameter optimization. And now you set for a particular lambda, you compute your model, you compute your f hat, and then based on validation data, you judge the quality of this lambda. Then you pick your next lambda. Let's say lambda, the next one would be lambda equals 0.5. And you again compute your f hat. And on validation data, you judge how good lambda 0.5 is compared to lambda equals 0. And you continue, and you go on like that. I mean, of course, somewhere you have to stop. Now, the problem is if your data set is too small, what you have to do is k-fold cross-validation, which we have talked about before. So you distinguish your data set into k partitions. You take out one. You do your training on the blue ones, and you do your validation of your particular lambda value on the yellow one. And then you repeat this k many times, and you do not get one value, one loss for a particular lambda, but you get k many losses, and you just average them. And you do this for every lambda that you're interested in, and then you compare which one gives you the best loss. And that's the lambda that you then choose in order to deliver your model. Okay, so to summarize our linear regression. So we spent a lot of time on linear regression because it's super powerful, it's very simple, it scales very well to large amounts of data. Already with linear regression, we are expressive in that we cannot only learn linear functions, but also other functions. For example, linear ones, polynomial ones, piecewise linear, radial basis functions, etc., etc. So it's a large class of functions which we can learn even with linear regression. It's always learned based on this kind of expression. F of x is a feature function transposed times our beta. That's our powerful model. As a loss function, we typically have a squared error. And if we want to optimize prediction, we do some so-called regularization. So I talked about lasso and ridge, both are regularizations. And regularization is anything that fights over fitting. So we have a regularization term. Ridge and lasso are continuous versions of subset selection. Subset selection, I have not talked much about this, is oftentimes also necessary. For particular, when you do linear regression and you have correlated variables, then your performance is not so great. What would be correlated? For example, birth date and age. I mean, you can, obviously they are inversely correlated. Smaller number for birth date means higher age and vice versa. So get rid of one of these two features right from the beginning. And for this particular, your insight is of course sufficient. Right? You look at two, you see that's the same thing, just in a slightly different space. You throw away one of them. This is something you should always do. Sometimes it's very good to do a piecewise, to do a pairwise correlation between attributes. And if you determine that one attribute is correlated highly to another attribute, it may be good to throw out one of the two. You have to think about this, of course. You have to think about, is there additional information that's sometimes crucial, or can I really get rid of it? So this is part of the whole pre-processing step. But subset selection is quite often necessary. And yeah, sometimes we can work analytically for a rich. These are always nice questions in an oral exam. I mean, very often one will do stochastic gradient descent or quadratic programming for lasso. We don't talk about quadratic programming here in this course, but we will talk about stochastic gradient descent. Okay, questions about linear regression at this point? Does not seem to be the case. Then let's look at logistic regression. And as the name suggests, logistic regression builds on and modifies linear regression to connect these linear models with classifiers. And there's a couple of things which we learn here that we will also use, for example, when we talk about neural networks. Again, we always try to see how are things cross-connected, right? Because this is the important part about this lecture, that you see the connection points, that you see, okay, we do regularization here. How do we do regularization in decision trees, in neural networks, in whatever, yeah? So almost every question that you ask for one technique, you could in some modified way ask for another technique. Okay, one step back first, what do we want to do? We want to classify. And classify means we have, for example, two classes. You can imagine whatever is here on this scale. I mean, this could be age and weight, and this could be male versus female, or it could be our dog example, anything. Doesn't really matter, right? It's just that you have two attributes and you try to classify into yellow and blue classes. So we have here two scenarios. The example is taken from the book by Hastie. And in the first scenario, the training data in each class, so for the yellow class and for the blue class, was generated from a bivariate Gaussian distribution with uncorrelated components and different means. So we have basically the yellow points. They came from a normal distribution with a mean of some x1 and x2, or I should maybe have said more common to say mu1 and mu2, and some covariance matrix. And this covariance matrix even has a particular shape, something like lambda 1, lambda 2, 0, 0. So that, and this normal distribution, now this for yellow, a similar one, but with different means and different covariances for the blue, generated the samples. So which basically means that for yellow, you have, for example, such a kind of normal distribution in 2 dimensions. This is the mean, this is the first standard deviation, this is the second, and these are 3 standard deviations in these 2 directions. And now you sample, and of course most are close to the mean, but there are some points that are also further away from the mean value. And you do this with the yellow distribution, and you do this with the blue distribution. You generate samples. I mean, if you think of males and females, and you would, for example, of course, weight and height may differ a little bit, but it's very close to each other. So, and now you want to classify just based on these 2 attributes. This is one possibility. And another possibility, scenario 2, is the training data in each class comes from a mixture of 10 low variance Gaussian distribution. So for example, yellow would come not from 1 normal distribution, but from 10. And each one of them would be something like this. And likewise for blue, and of course we would have 10 center points and 10 low variance distributions. This is quite often a plausible model for a population, because you could think, okay, people or dogs or whatever you want to classify. Let's say cars. Cars come in different lengths and sizes, and trucks come in different lengths and sizes, and there is somewhere a dividing line between trucks and cars, but actually at the borderline it's quite blurry. And of course we have very small cars, they might come here, and we have very large cars, maybe they would be here, and somewhere there's a borderline to the trucks, but they come in different flavors of length and weight. And so you could say every kind of flavor of car, whether it's a sedan or whether it's a pickup truck, would have come from a different normal distribution. Usually, when we see such data points, we don't know, does my distribution come from 1 normal distribution for the yellow class, or does it come from 10? We just don't know. I mean, we can try to investigate, but in the general case, we don't know. So all what we see here is such a picture. And now we want to classify and say which point that we encounter newly should be yellow and which should be blue. So what do we know about loss functions so far? We didn't specify the loss functions explicitly for k and n. We tried to optimize the k to have a lot of correct classifications, but we didn't specify. For regression, we typically looked at least squared error. And now what we want to do is we want to have a bit of more systematic approach for what a loss function. So the expected prediction error for numeric variables and the mean squared error was the expected difference between y and our estimated function squared. We could also do this as an integral over the different values squared as we go over the probability of observing certain x and y values. And when we do this, what we learn as a function f hat is the expected values for y given that we observe a particular x. So the conditional mean for a particular value, we get a particular y value as a response. The conditional mean is the best solution that we can get at. We can also, instead of taking the square here, the square error, look at the absolute error. Actually, what we get then is not the average y, but we get the median y for a particular x. Just to give you an intuition how the two might vary, we could look, for example, at age and income. Let's say we want to predict age and income, then age would be here and income would be here. Let's say we have someone like at the age of, I don't know, maybe 70 or so, Bill Gates would be somewhere up here. Maybe Zuckerberg would be also likewise, but much younger. I think he's younger than me. Maybe somewhere like here or higher, I don't know. So, and most people, of course, maybe most people would have an increasing income, but at a very low, in a very low area, compared to at least to the billionaires. Now, if I learn for a particular age, the conditional mean, I might predict, knowing nothing else, that this person should earn like this, because this is like the mean value of all these low values here and Zuckerberg. For the median, of course, I would rather predict something here. Yeah? So obviously, the mean and the median that I would predict would be different solutions. Which one is better depends on your application. I mean, this one is typically easier to realize. And yeah, this is not much used in practice because of differentiability. Okay, now let's talk about classification. And for classification, what is our loss? We can represent our loss by the confusion matrix. You remember the confusion matrix? Confusion matrix basically said like how many people classified we into one class, although they could be in a different class. And now if we classify object, whatever, into the wrong class, then we have a particular loss with that. So if we have an object classified into class 1 and it was class 1, then it's a 0 loss. But if an object 1 is classified into class 2, then we have this loss 2, 1. And if an object should have been in class 2 but is classified in class 1, it would have the loss 1, 2. So every time we do a misclassification, we have a loss. In the simplest case, all these numbers would be 1 and only on the diagonal we would have a loss of 0. It depends. If we have the mushroom data set, then we might have 3 classes, edible, poisonous, and doesn't taste good. So if I predict edible and it doesn't taste good, okay, maybe there is some loss to that. But if I predict edible and it's poisonous, then my loss is much larger. So you see how a certain confusion may be punished differently. And this we can nicely put into such a matrix, which is a loss matrix, depending on how I confuse the true result with the predicted result. Yeah, very, very often, all that we do is a 0-1 loss. Either it's 0 loss because an object is in the right class, or it's a 1 loss because it's confused. Now, when I take such a loss matrix, like 0-1 loss or this one here, what is now the expected prediction error for a certain function f hat that I learn, a certain classifier that I learn? it's the expected value for being in the different places of this loss matrix. And so I go through all the positions and I look at how probable is it that I get an object and I classify it in some way. And as my time is over, that's where we will look at in the video recording next. And then if you have any questions, write them up, post them in the forum, or ask me when we see again in 3 weeks. Have a